Hello, and welcome to section 3.4, where we're going to be looking at the idea of rates of change. Again, we have seen rates of change before back in chapter 2, but now we're going to look at them in some new contexts because we have this new thing to work with called the derivative. So, a little refresher to start out here. We're going to recall our different types of rates of change. The two main types were average rate of change and instantaneous rate of change. So if we're given a function y equals f of t, we can define the average rate of change, AROC, remember? So the average rate of change of that function f with respect to t over the interval t1 to t2, all right, this is going to be our average rate of change formula from chapter 2, remember? But now notice that we are using the variable t instead of the variable x. And the reason for that is because in this section, a lot of the things we're going to be looking at are changing over time. And so we're going to use that variable t to represent time here. So it's just the same idea, just t instead of x. So our average rate of change is going to be a calculation of the change in y over the change in t, which we could write as f of t2 minus f of t1 over t2 minus t1. Okay, hopefully that is a familiar formula. We've seen it before with the x's instead of t's, but it's the same idea. That's our average rate of change formula right there. And note that it's also the formula for something else, right? And this is also a slope formula. So this is the slope of the secant line. Okay, so a secant line, because we have 2 points that we're looking at. So this is between the 2 points on the curve, t1 comma f of t1, that's our first point. And then the second one is t2 comma f of t2. Okay, so yeah, that's our slope of a secant line, average rate of change formula for f as a function of t. Okay, now we're going to use that and remember how we came up with an instantaneous rate of change. We did that by moving t2 closer and closer to t1. Or back in chapter 2, we would have said we moved x2 closer and closer to x1. The overall idea there is you want your 2 points to move closer and closer together until we get that limiting case of closeness, where the 2 points are right on top of each other. So we're going to take a limit as delta t approaches 0. Delta t being our change in t, so that is t2 minus t1. And we want that difference between those two values to go to nothing, essentially. So the points come right on top of each other. And when we do that, we're going to get our instantaneous rate of change of f with respect to t. We could write that as a limit as delta t approaches 0 of delta y over delta t. Okay. And then we'll put in that formula. Remember how we did it back in chapter 2? We kind of turned this around a little bit so that we would just focus on one point. And here we would have the fact that T2 equals T1 plus delta T. Okay, so we would have f of T1 plus delta T minus f of t1 all over delta t, because that's the t2 minus t1 thing in the denominator there. Okay, this is t2 getting plugged in. But now we can recognize this as a definition of a derivative. It's just that we have delta t written down there instead of h. Okay, so usually we have limit as h approaches 0. Now we're letting delta t approach 0. So this is going to be f prime of t, or dy dt, depending which notation you like. But the overall idea there is that this is referring to the derivative. All right, so the derivative provides an instantaneous rate of change. Okay, and note that this also would provide the slope of a different type of line. So this is the slope of the tangent line at the point t1 comma f of t1. Okay, so yeah, you'd use our old average rate of change formula, slope of the secant line to find average rate of change of any quantity, and then you would use the derivative now to find an instantaneous rate of change.